we've got a bunch of stuff to figure out about two vectors, u and v, mainly the dot product, whether they're orthogonal or not, and the orthogonal projection of u onto v. Okay, so the difference here between what we're looking at and the last video I did on this is right here. It's not much. It's just that these guys are in principal vector form, which doesn't really make it any harder to work with. Let's just get through this one. Now, the magnitude of u is very easy, right? If you remember Pythagorean's theorem, this looks very similar for a reason we've talked about in class. You square the components, add them together, take the square root, and there you go. So for us, this is the square root of, let's see, 5 squared plus 2 squared. Okay, what is that? 29. Okay, great. So the magnitude of u is the square root of 29. For v, same idea. Okay, we're going to take the magnitude of v equal to the square root of the sum of the squares of its components. So that equals, let's see, the square root of vx is just 1 squared, and vy is negative 5 squared. Okay, so multiply those together, you're going to get radical 26. Okay, easy peasy. Now let's move on to the dot product. If you remember, there's two definitions of the dot product. They're both extremely useful. I'm going to use this first one for this problem. It's the product of the components in the x direction plus the product of the components in the y direction. Okay, so I take the x components, multiply them together, I take the y components, multiply them together, add them all up, and I get my dot product. Another definition, equally useful, is it's the product of the magnitudes of the two vectors times the cosine of the angle in between them. Okay, so first definition first. Let's take the x components. This is going to be 5 times 1. I'm looking at the I principal vector there. And now let's look at the j principal vector. This is going to be 2 times negative 5. Okay, well, if you multiply those together, add them up, you're going to get negative 5 for the dot product. Okay, that's a nice tidy number. And the magnitudes of them we already figured out before. So this is going to be the square root of 29 times the square root of 26 times the cosine of the angle. That's what we want, that angle. So we can just rearrange this to say the following. The cosine of that angle that I want, the angle between the two vectors, is equal to negative 5 divided by square root of 29 times the square root of 26. Okay, no problem. We're going to take the arc cosine of each side. So what you're going to punch into your calculator is going to look something like this. Arc cos, or inverse cos, whichever you prefer, of this thing. And you could say negative 29 times 26 inside the radical if you want. What I get for that, when I go through all the calculations, is uv equals, or theta uv equals 100.49 degrees, okay? 100.49 degrees. Now, it's common to make mistakes. It really is. Your job as a mathematician is to catch the mistakes. That's what's going to set you apart from every other bozo who's making mistakes. What you do here is a basic sanity check. I'm asking, is this angle of 100 degrees reasonable? Does it even sound right? Well, think about what u is. It's 5 over and 2 up. So something like this. There's u. And what's v? Well, that's 1 over and 5 down. So, I don't know, kind of like this. There's v. And the angle between them being 100 degrees. Does that sound about right? Well, there it is. You tell me. It looks like it's almost 90 degrees. It's pretty close. So I think this is a pretty good estimation. Now, since we've figured out what the angle is between these guys, our next question is, are they orthogonal? And I want to focus on that word. That is a pretty important word. And the further you get into vectors, the more important it gets. What orthogonal means is perpendicular. Are these two vectors perpendicular? Okay, to be perpendicular, the angle between them would have to be equal to 90 degrees. That's the definition of a right angle. And it clearly is not. It's 100 degrees. So this is a big old no, not orthogonal. Now the last thing we have to do is calculate the orthogonal projection of u onto v. I just want to start off with a very quick explanation of what that even means. If I have two vectors, I'll just use these vectors. There's one, there's the other. These are, you know what, I'm going to make something up because I don't like the shape that I'm going to get from this one. There we go. Here's my two vectors, v and we'll say u. If I want to figure out the orthogonal projection of u onto v, what I do is I drop a perpendicular line down onto v from u, and then I just draw a vector right there, in line with v, the portion of u which is in the same direction as v. That's what a orthogonal projection of u onto v is. Now, sometimes you get positives, sometimes you get negatives. Don't worry, it's kind of a nasty equation. Fortunately, at this point, we've calculated just about everything we need for it. So here's the equation that's going to be useful for you. Projection of u onto v is equal to the dot product of u and v divided by the magnitude of v squared times the vector v. So most of these things we've already calculated above. I know the dot product is -5. I know the magnitude of v was square root of 26. Square it, you get regular 26. And then the vector v, what was that? I minus 5j. We're in component form. So I minus 5j. Well, this is very easy to multiply. You just distribute. So this becomes -5 over 26i. And looks like we're going to have a plus 25 over 26j. Okay, that is your projection of u onto v.